Okay, this is on dividing radicals and the simplified form of radicals. Okay, so let's look at an easy one to start with. So if I have the square root of 75 m to the third divided by the square root of 3m to the second. Now, we talked about the division property last week. Okay, we learned that if they were both the same root or the same index on the radical, then we could rewrite these if we wanted to underneath one radical if it helped us. And in this case, I believe that it does help us because 3 is a factor of 75. How many times will it go? 25. And m squared will cancel into m to the third and leave you with an m. So you're going to get the square root of 25m. The square root of 25 is 5, and then you still have the root m left there. So you can use that property that we talked about last week either way. If it were like this and it helped us to break it up like this, we could. If it were like this and it helped us to break it up or to put it together like that, we could. Okay? So it's just kind of whichever way works to make your problem simplify. Okay, let's look at this one. The square root of x to the 6th over y to the 12th. Now those are underneath one radical, but I'm not able to simplify them into each other like I was up here. So this would be handy for me to break it apart like this. The square root of x to the 6th over the square root of y to the 12th. The square root of x to the 6th is x to the, remember you take the power and divide it by the index, so 6 divided by 2 is 3, and 12 divided by 2 is 6. So that was handy to use the reverse of the property. Do you have a question? Okay, what if maybe one of them, well, I shouldn't say that because I was going to say, what if one of them was a perfect square? But those were both perfect squares. I was able to square root them. So let's do one that's a little more complex but very similar to that. So the square root of 16y, all under a radical with 25x to the 4th in the denominator. Break it up into the square root of 16y over the square root of 25x to the 4th. The square root of 16 is 4, but the y stays inside there because it's not square rootable. The square root of 25 is 5, and the square root of x to the 4th is x to the 4 divided by 2 is 2. Your division property can be applied to two radicals as long as they have the same index. So they must have the same index to be able to use that division properly freely. Let's do another example. We have the square root of 98y to the 4th over the square root of 2y. If you see that they're in separate radicals but they have the same index, and you notice that they are divisible, one is divisible by the other one, then you want to go ahead and put it under one radical and do that division to start the simplification process. So I know that 2 goes into 98 49 times. And y goes into y to the 4th, y to the 3rd. Now, we got to remember what we did last week. The square root of 49 is 7, so that's pretty easy, right? But what about that y to the third? We break it down into y squared times y, remember? Because it has to be the exponent has to be divisible by the index a whole number of times, okay? And it is not. So you go to the one that is below the exponent, so the number that is below the exponent that is divisible by the index. This index right here is understood to be 2. So we went down to 2. So the square root of y squared is y, 7y, and then you have the root of y left inside. So this one comes over. Okay, not always do they work out beautifully where the denominator divides into the numerator, okay? They don't always work out like that. In which case, we have to incorporate a strategy that's called rationalizing the denominator. Now, we use that when there is a radical in the denominator that you can't make go away by doing all this business with it, by dividing and simplifying and all that. So what I'm trying to say, and I don't think I'm doing a very good job at this moment, is no radicals are allowed to be in the denominator. No radicals can remain in the denominator. So when you've simplified all you can and you still have a radical, then we have to use the process that's called rationalizing the denominator. And I like to tell my students that when we rationalize something, we try to make it okay. So that's what we're going to do. We're going to make this denominator okay. We're going to do so by multiplying the numerator and the denominator by the same radical that, and I'm going to just put it out there, that we have to think of. That will simplify your denominator. So that no radical remains. Now I'm making this up on the fly. I'm sure you couldn't tell. But I didn't find a good little sentence in the workbook to go by. So I'm going to show you how to think about it. It's all based on what you already know about radicals. So this should fall into play pretty good. If you look right here, you noticed that 25, you were able to take the square root of 25. And you were able to take the square root of x to the fourth, right? So it's imperative that whatever is underneath the radical in the denominator can be done. And that's not a proper verb. But we want it to be square rootable if there's a square root down there. We want it to be cube rootable if there's a cube root down there. We want it to be fourth rootable if it's a fourth root down there. So you want to be able to take that root of whatever is under that radical. And if there are not enough factors of that under there, then we are going to multiply by how many we need to make it happen. Okay? Deep breath. Here we go. Y. Oops, let me use a different color so that it doesn't blend in with my directions. So y over the square root of 5. This is a very simple example to start with, a perfect one to start with. Can you take the square root of 5? Now, I don't want decimal approximations. Can you take the square root of 5? No. Okay? So, we are going to rationalize the denominator by multiplying the numerator and the denominator by the same radical so that we're going to have to think of it, so that we'll simplify the denominator so that no radical remains. Okay, what can I multiply 5 by that will create a perfect square since I'm square rooting? 5. Not just 5, I need to multiply it by the square root of 5. What is the square root of 5 times the square root of 5? It's the square root of 25, which is in its most simplified form what? 5. Does 5 have a radical on it anymore? No. That was my purpose. Whatever I do to the denominator, I have to do to the numerator. Okay? Because, in essence, I want you to look at what you're multiplying by. You're taking this fraction, y over root 5, and you're multiplying it by 1. Isn't the square root of 5 over the square root of 5 equivalent to 1? Can I multiply anything by 1 and still get the same thing I started with? Absolutely. Okay? So this is legal because I'm just multiplying by 1, but I'm doing it in a sneaky little fashion. I'm rationalizing. I'm saying, but I didn't mean to, but look, it worked anyway, right? I'm sorry, Mom. I'm sorry, Dad. I'm sorry, husband, boyfriend, girlfriend, whatever. It just happened, but look, it's going to be okay. That's what you're doing here. You're rationalizing within a fraction. Okay? Did you like that? Y'all didn't know I could be dramatic, did you? Okay. So, y times the square root of 5 is y root 5. It's okay to have 1 in the numerator, just not in the denominator. Why? Why? Well, because it just isn't. Just not proper. In math, we have things that are proper and things that are improper. It's just not proper. Okay? And the square root of 5 times the square root of 5 is 5. Now, it's the square root of 25, which is 5. Okay? Do you have a radical down there anymore? No. Do not put 1. It's not always itself that you multiply by. So when I always start with an example like this, students automatically assume that you multiply it times itself. Not if that doesn't get the job done. Okay, so you have to analyze what's down there and multiply it by whatever will cause it to be rootable, by whatever root it is. And I don't even think that's a real word, but I think y'all know what I mean, right? When I say square rootable, cube rootable. Okay. So let's look at this one. 7 over the cubed root of x. We got a cube root now. So I can't just multiply by the cube root of x, because if I do, that's going to give me the cube root of x to the second, and I'm in no better shape than I was to begin with, because you can't divide 2 by 3, okay? So how many factors of x are currently underneath this radical? How many do you see right there? 1. The exponent is 1. You can't see it, but it's there. That's why it's 1, okay? How many do you need? How many more x's would you need to be able to take the cube root of this term, or this factor that's under here? 2 more? Does everybody think that you need 2 more x's? If I have 1x and I had 2 more x's, how many x's would that give me underneath the radical? 3. Can I take the cube root of something to the 3rd power? Yes. So that is why you have to reason through it. So it's the cubed root of x squared. So your answer on the top is 7 on the cubed root of x squared. It cannot be simplified. On the bottom, you get the cubed root of x cubed, which is just x. And you walk away from the situation going, I played that pretty well. I teach teenagers all day. And I have one that lives with me. Okay, let's do some more. This is fun. I love these problems. You do this one by yourself. Okay, so I have one factor of 7 under there, but I need how many to be able to take the cubed root of it? I need 2 more. So I'm going to multiply it by the cubed root of 7 squared. Don't change it to 49, just leave it like it is. So down, now up here you're going to want to change it to 49 because you're simplifying that. Okay, so x, and then the cubed root of 7 squared, I mean you can't do anything else to it, so that's the least you can do to it is go ahead and square that out. But down here, this is the cubed root of 7 cubed, which is just 7. Okay, let's look at one that maybe isn't quite so simple, something that's a little more complex. If we have the square root of d over, let me use a different color, starting to run together, the square root of d over 18. There's a couple of ways you can do this problem. You can start by simplifying the square root of 18, or you can just ask yourself, what do I need to multiply 18 by to get a perfect square? And it doesn't have to be itself. 18 is a number that's made up of a lot of factors. If you think about 18, it has a perfect square factor in it of 9, doesn't it? Let's go through some multiples of 18. 18 times 2 is what? 36. Is 36 a perfect square? Sure is, isn't it? So why don't I, first of all, let's break it up into the square root of d over the square root of 18. You don't have to show this step if you don't want to where you break it up, but I'm just trying to be consistent with what I'm writing. So if I multiplied this times the square root of 2 over the square root of 2, will that make my radical go away in the denominator? What do I get? I get on top the square root of 2d, no biggie. In the bottom, I get the square root of 36. What is that? Did my denominator go away? Did my radical in my denominator go away? Yes. It did, didn't it? Now I'm going to show you another way to work that problem. I want to work it 2 ways for you, okay? So when you get to it and you go, I don't know which way to start, you're kind of conflicted, it's okay because there's 2 ways you can do it. So I'm going to break it up again, and it's the square root of d over the square root of 18. And then I'm going to say, well, I know to start with, notice I put an equal sign, that 18 breaks down into the square root of 9 times 2. And the square root of 9 is 3. Right? Okay. So now the only radical that I have to worry with is this square root of 2. So I'm going to rationalize my denominator by multiplying by square root 2 over square root 2 because I have 2 to the first power, so I just need another 2 to be able to take the square root of it. And then I'm going to get the square root of 2d over 3 times, what's the square root of 2 times the square root of 2? 2, isn't it? It's the square root of 4, which is 2. So did I get the same answer that I got up there? I did, didn't I? It's running off the page, I'm sorry. Can y'all see that I got the same thing though? So you have 2 ways. Now here's the deal. If this is a little foggy and you're like, go back and watch the video, okay? You can fast forward to this part to get to where you need to go, but make sure you're making use of those videos. All right, let's do one that's more complex than that. So I have 6 over the 4th root of 4xy squared z to the 3rd. I'm doing the 4th root. I would like for you to think about 4 as 2 to the 2nd power. Well, you can. Yeah, that would be the easiest thing to do here because it's a 4th root. I didn't have to think about 9 as 3 to the 2nd power here because I was square rooting, and we're real comfortable with square roots, but we're not as comfortable with 4th roots and stuff. So when the indices get bigger, I usually just start breaking my coefficient down into prime factors. Okay, so I'm going to rewrite this problem as 6 over the 4th root of 2 squared x y squared z to the 3rd. And this way you can easily see how many more of each factor you need to be able to take the 4th root of it. So if I have 2 to the 2nd, but I need to be able to divide by 4, how many more 2's, how many more factors of 2 do I need? 2 more, right? I've got 2 factors of 2, I need 2 more. So I'm going to rationalize by a radical. It'll be the 4th root of it. 2 to the 2nd. That'll give me 2 to the 4th, which I can take the 4th root of it. Okay, I have an x to the 1st, so I need 3 more x's. Does everybody agree with that? Because you need them to be 1 plus 3 makes 4, and 4 is divisible by 4, right? I have 2 y's. How many more y's do I need? 2 more to make a total of 4. And then I have z to the 3rd, so I only need 1 z to make a total of 4. Now I'm going to show all these steps very carefully. So in my denominator, I now have, and like I said, I'm going to show all these steps. I'm going to make it, this is kind of like going backwards a little bit. But I want to do it because this one's so complex. So it's the fourth root of 2 squared times 2 squared is 2 to the fourth. Just leave it like that. X to the first times x to the third is x to the fourth. Y to the second times y to the second is y to the fourth. And z to the third times z is z to the fourth. I'm not even going to fool with my numerator right now. I just want to concentrate on this denominator and what I set out to do, which was to get rid of the radical. Now I have the fourth root of each one of these to the fourth. You know that the fourth root of anything to the fourth is itself, right? So in my denominator, I no longer have a radical, and I have 2x, y, z. In my numerator, I need to realize that I can't simplify any of this. So the 6 is going to stay outside. I'm just going to come all the way over to the end, if that's okay. And I have the fourth root of 2 squared is 4. You do want to go ahead and simplify it now that you're writing your final answer in the best form possible. So there's your answer. Any questions? That's a tough problem. I left this blank intentionally because I didn't want to write the same thing twice. Okay. Now, remember when we talked about multiplying conjugates? And when we multiplied a plus b times a minus b, we only had to do the first and the last. So we would always get a to the second minus b to the second as our final answer. So just a quick review, if I had x plus 4 times x minus 4, then I'm going to end up with x squared minus 16, because the O and the I, the outer product and the inner product, always cancel out when you're multiplying conjugates. That's going to parlay into rationalizing denominators that have 2 terms in them, okay? So we'll start with this one. 2 over the square root of 5 minus 3. This is different from these things that we've been doing. Please look at the denominators of all that we have done. They were very simple. There was no plus or minus signs in them, was there? This is a 2-term polynomial. It's a binomial. When you are faced with a binomial that has radicals in it in your denominator, you're going to multiply by the conjugate. The conjugate of a plus b is a minus b. The conjugate of x plus 4 is x minus 4. And the reason you're going to do that is because when we multiply the first times the first, or square the first term, it's going to take away any radical that might be in there. So, what is the conjugate of root 5 minus 3? Use this as your guide. What's the conjugate? Root 5 plus 3. So you're going to multiply by root 5 plus 3. And whatever you do to the bottom, you do to the top. Because you're just multiplying by 1, it's really okay. All right? That's what you're doing. And then let's talk about the denominator. What beautiful thing happens. It is so pretty. The square root of 5 times the square root of 5. Remember, they're conjugates, so you only have to multiply the first times the first and the last times the last. You only have to I had a student my very first year of teaching come up with that. He said, oh, we just fluff. Yeah, that's all you do. Okay? So square root of 5 times the square root of 5 is 5. No radical. It's gone, isn't it? Isn't that lovely? And then negative root 3 times, I'm sorry, I said that wrong. Negative 3 times positive 3 is negative 9. Just continue working in my denominator. 5 minus 9 is negative 4. Well, it doesn't get much simpler than that, does it? And here I have a monomial times a binomial. So I have to use my distributive property. 2 root 5 plus 6. So I have to do 2 times this and 2 times that. Now, generally speaking, we do not leave a negative in the denominator of a fraction. So chances are this will be pulled up in the middle. And I cannot answer the question, will it mark it wrong if you leave it down there? I really don't think it will, but I can't say for sure. Wasn't that fun? Let's do another one. Your turn. Okay, you try that one by yourself. What's the conjugate? Square root of 15 plus 4. Okay, so top and bottom. So the denominator guides you into what you're going to multiply by. So 1 times that, that's pretty easy. I can just go ahead and write that, can't I? I probably shouldn't have because I'm going to have to come over. But, okay, here we only do the first and the last, right? The square root of 15 times the square root of 15 is 15. Negative 4 times positive 4 is Okay, so this is negative 1. So I have the square root of 15 plus 4 divided by negative 1. What does that do? What does it do to these two things? You can't leave it over a negative 1. Changes the sign. So this would be negative root 15 minus 4, wouldn't it? So you can't leave it over a negative 1, just like you can't leave something over a 1. If you're dividing by a negative 1, it just changes the sign on everything. Okay, so let's do one more that's much more difficult. And I believe this will be the last problem for tonight. Yes, it will. Okay, 5 square root of 2 minus the square root of 5 over 5 square root of 2 plus the square root of 5. Now, you're probably going, those are conjugates of each other, but they don't do you any good if they're top and bottom, right? So I still have to rationalize this denominator. You're going to multiply by the conjugate of the denominator, which is 5 square root of 2 minus root 5. And whatever you do to the denominator, you do to the numerator. Now, it's very important that you realize this is a binomial times a binomial in the numerator, and you're going to have to use the FOIL property, or the FOIL method, I should say, not property. In the denominator, these are conjugates. I only have to multiply the first and the last in the FOIL method because the O and the I cancel out. So I only have to do 5 root 2 times 5 root 2, which is 25. So that's 25 times the square root of 4, which is 25 times, let me erase that. I'm going to show my work right down here, over here. So that's 25 times the square root of 4, which is 25 times 2, right? Which is what? 50. Okay? And then the square root of 5 times negative square root of 5 is negative. You should be able to go straight to 5 on that one, but it would be negative square root 25, which is 5, of course. If you need to show those steps, they are there for you. In the numerator, we have a mess. This is about to be a nasty, nasty mess. No way around it. That's why we saved it for last. So we're going to do first, outer, inner, last. Okay, 5 root 2 times 5 root 2 is 25, and I'm going to go ahead and write on the square root of 4 because it's going to be so messy that I just want to show the steps. Okay, outer, 5 root 2 times negative root 5 is negative 5 on the square root of 10. You multiply what's underneath the radicals times each other. Inner, negative root 5 times positive 5 root 2 is negative 5 root 10. And last, negative root 5 times negative root 5 is positive root 25. Okay, simplifying, 25 times the square root of 4 is 25 times 2. Minus 5 root 10 and 5 root 10 makes minus 10 root 10. And then the square root of 25 is 5. Again, you could have gotten to this part much sooner. And 50 minus 5 is 45. So this is 50, and 50 plus 5 is 55 minus 10 root 10 over 45. Now, you're probably thinking that you're finished. But when you get to this point in a fraction that contains radicals, you have to look at the numbers that are not under the radical. So all three, the first term, the second term, and the denominator. And if they can be reduced by a common factor, then you should reduce it. I noticed that 55, 10, and 45 are all divisible by 5, so you have to reduce it by 5. So it would be 11 minus 2 root 10. Now notice you don't touch what's under the radical though, do you? Okay, because it's different, it's special. And 5 goes into 45 9 times. Okay? I think it does. Did I do it right? Okay. All right, questions? It is late. That's part of it. You have to recognize that they can be reduced. It's just part of simplifying fractions. It's a lot. Algebra is deep.